delay. And hi again to everyone. My name is Felix, and the work I'm presenting was developed together with Gert, Smolka, and Yannick Forster, starting out of my bachelor thesis at Jahn University. And as stated, this is declared as a proof pearl. So we'll have a lot of focus on the proofs, of course. But during the work, we also came across some, I would say, interesting foundational and conceptual aspects that I also want to address. So the talk will always be a little bit switching between those two aspects, the proofs on the one hand side and the foundational aspects on the other side. And the first aspect of the title is the Cantor-Bernstein theorem. And to get everyone again on the same page, let's quickly recap what the Cantor-Bernstein theorem says. It talks about two sets, A and B, that have injections between each other. So an injection from F from set A to B and from B to A. And then it says that then there's already a bijection. And also the history of the theorem is, I would say, quite interesting. In 1878, it was firstly published by Cantor, however, yet without a proof. And the first proof was then published 10 years later by Bernstein, however, crucially relying on a consequence of the axiom of choice and also classical logic. 10 years later again, there was a further proof by Koenig, who does not rely on choice axioms, but heavily on the law of excluded middle, so again, classical logic, and therefore the anti-constructive character of the theorem was quite early pretty clear. And then, around 4 years ago, it were Pradic and Brown, who indeed proved that the Cantor-Bernstein theorem implies the law of excluded middle, so classical logic is indeed necessary to prove the Cantor-Bernstein theorem in its full generality. Lastly, I also want to mention the work by Escardó, who worked in homotopy type theory and formalized, of course, then using the law of excluded middle in homotopy type theory and with the unique choice of homotopy type theory, the theorem. And the natural question that now somehow arises is, well, if this theorem is classical, do we can find a restriction or a formulation of the theorem such that it becomes provable fully constructively? And this is also a question that Martin Escardó treated. He gave the challenge whether one can find a formulation of the Cantor-Bernstein theorem such that it becomes provable fully constructively for not only finite sets, for which it is quite easy to prove. And in fact, we were able to at least partially answer the question with our work, because we considered types that are on the first hand enumerable. So there's a function going out of the natural numbers that's image are exactly all the elements of the type and who has decidable equality. We call this discrete. So there is a decider function for the equality of the elements of the type. And for those kind of types, so for types X and Y that are enumerable and discrete, we can indeed prove a constructive version of the Cantor-Bernstein theorem, talking about if we have injections, then there is already a bijection. Fully constructively and not relying on any classical logic. But I think also for those of you who work, for instance, in Lean or Isabel, the proofs can also be interesting because they are on the first hand quite elementary. And secondly, they yield also quite interesting mathematical and also computational insights. But before we go to the proofs in detail, I quickly want to talk why we were actually interested in this topic. Because we came from a bit different direction, namely so-called synthetic computability theory. And the rough idea of synthetic computability theory is to work in a setting of only computable functions. So you work in a setting where you know or you can assume that all functions that appear are already computable. Constructive settings are therefore, of course, good candidates, as it was explored by Richman and Bauer. And we now work in the constructive type theory of Cog, the calculus of inductive constructions. And why we were so excited or are so excited about synthetic computability theory becomes maybe clear if we look at basic notions from computability theory, for example, the many-one reduction. In our setting now, we talk about predicates instead of sets that reduce to each other, and we call a predicate, and we say that a predicate P, many-one reduces to a predicate Q. As you might guess, if there exists a function f from x to y, such that this pointwise equivalence holds, if Px holds, then if and only if Q of the function value holds. And if you think back at your computability class, you might notice that there is a requirement omitted for the function f, namely that this function f is computable in some kind of model of computation, for example, Turing machines or so. But this is fully okay, exactly due to our synthetic setting, because we already know that all functions that appear are assumed to be computable. And this now is, of course, really well suited to formalize and mechanize results from computability theory, because we do not have to program this annoying Turing machines and so on. And indeed, we were able to formalize not only basic results, but also look at different undecidability proofs for different problems, also at post-problem for many one reductions and truth table reductions, and look, of course, also at Turing reductions, and Gödel's incompleteness theorem also synthetically. And what we were also interested in was the so-called Myhill's isomorphism theorem. Myhill looked at not many one reductions, but one reductions that refine the notion of many one reductions. So it's exactly the same definition, however, additionally requiring this function f to be injective. So if we have two function values that are equal, also the x values are equal. And for the whole paper and also the remainder of the talk, if I say injective function, I mean exactly this definition of injectivity. And with this 1-1 reduction, Myhill formulated his isomorphism theorem, again for enumerable and discrete types, and two predicates P and Q. And he says if those two predicates 1-1 reduce to each other, P to Q and Q to P, that then there exist functions f and g that again fulfill this pointwise equivalence and that invert each other, though in fact f and g are bijections. And the proof is, I would say, quite interesting and beautiful. It goes back again to Myhill, and we mainly followed the excellent textbook presentation by Rogers and formalized the many implicitly given arguments in the traditional presentation. And the main idea is to work with so-called correspondence sequences. You can think about a correspondence sequence as a finite or partial representation of a bijection. And we say that the list of pairs is a correspondence sequence for those predicates P and Q, if we again have this pointwise equivalence. And we have some kind of 1-1 property stating that for two pairs, their first components are equal if and only if their second components are equal, which ensures that no component is mapped to two different other components. Maybe it becomes more clear if we look at an example. We have here a correspondence sequence with the meaning of the colors right there. So the brown pairs are, for instance, those where the predicate holds, and the violet ones where it doesn't hold. And you see that there are no duplicates in the list, so also the 1-1 property is fulfilled. And now the crucial idea of the proof is that if we have a 1-1 reduction and we have some function f, like there as an example, that we then can extend and therefore approximate the final bijection. So if we have a correspondence sequence and a fresh element f, we now can use this injection to travel through the correspondence sequence. So we apply the function f, use the correspondence sequence to again get a letter, apply again the function f, and so on. And by the 1-1 property of both the function f as well as the correspondence sequence, we know that this terminates with a fresh element, in this case the element 2, and we can add this new pair f and 2 to the correspondence sequence and thereby extend the correspondence sequence for a new pair. And if we have now two reductions in both directions, also this extending is possible in both directions. And therefore, we can approximate and converge against this final big bijection by using this extending of correspondence sequences. So we begin with the first element at the first letter, we add the first number, and then again the first letter, and so on, the second number. And now a little edge case, if now you notice the third letter is already added, we can simply skip this step and continue directly with the third number, and so on, and thereby converge to the final bijection. This argument goes back to something already Cantor did. It has the name of back and forth argument because it's always this back and forth between, in this case, the letters and the numbers. And motivated by our work, also Dominic Kirst published a paper about further examples of back and forth arguments. And as I said, this converges now to the final bijection and is also possible for infinite types because we know that in the nth step, the nth element is added to the correspondence sequence, and this proves then exactly the isomorphism theorem of Myhill. But now let's take a step back and look what we actually are doing here. So as I said, we work in a constructive setting, which is then used to formalize results from the synthetic computability theory. The result in this case was the isomorphism theorem. But you might already notice that if we instantiate now the theorem with the predicates that always hold true, it's a little finger exercise, we result in exactly the formulation of the constructive Cantor-Bernstein theorem, talking about injections, if we have injections that we then already have a bijection. And if you now look at especially the Cantor-Bernstein theorem in this formulation, but actually also its isomorphism theorem, this is now a result from constructive math, as also Escardó asked. So therefore, we are not only using the constructive setting to formalize results from synthetic computability theory, but those results again yield results from constructive math. And that results from constructive math can be understood computationally, is quite well known. But in our case, we now go somehow the other way around, at least morally, and turn results from synthetic computability theory in results from constructive math. And this motivated us to have again a closer look at the Cantor-Bernstein theorem. I briefly gave the intuition of the first proof via Myhill's isomorphism theorem. And we looked also for direct proofs. Again, we have the same setting and the same idea to converge against the final big bijection. And now we have again the correspondence sequence or the partial representation of the bijection, a fresh element. But now the extending works in a different way. We use this injective function to map to a larger list than the list of the second components. And because it's an injective function, we know that this list is duplicate free. And by pigeonhole principle, we know now, because this list is duplicate free and longer, that there must be an element that is not down there, and therefore find a fresh element, again the 2, and can again extend the partial representation of the bijection, and again extend the representation. So this yields a second proof via this pigeonhole principle, and then we also constructed the kind of canonical bijection, where we simply map the first letter to the first number, the second letter to the second number, so exactly what you might expect, and where the injections only are used to prove the termination of this algorithm. All right. Lastly, I want to quickly talk about what might happen in other foundations. Because, as I said, we work in Cox type theory, but we're not relying on some specific properties of Coq, like in predictivity or large elimination principles. The only thing that we use, crucially, is what is called in constructive math the so-called delta 0-1 choice. And it says that if you have a type that is enumerable and discrete, so exactly our setting, and a binary predicate that is decidable, for that we know that if we have for every x there exists y such that the predicate holds, that you can then define a function, so not only the existence statement, but a function for that the predicate holds. And as I said, this is provable in Coq by induction on a so-called accessibility predicate. An equivalent formulation of this delta 0-1 choice is, can be found in Coq's standard library. But also in other constructive type theories, like Martin-Löf type theory, it is provable because there the meaning of a for all exists statement is already a function. And also in homotopy type theory, it is provable as a consequence of the unique choice. So we would claim that our results are not only provable in Coq as we did it, but also in other constructive type theories. So let's summarize. We looked at Myhill's isomorphism theorem and a constructive restriction of the Cantor-Bernstein theorem. We proved this fully constructively and formalized and mechanized the proofs in Coq. And we would claim that the results also should transport to other foundations. And I want to conclude with this idea, this conceptual idea we used. We worked in a constructive setting in order to formalize results from computability synthetically, and then turned those results were yielded again results from constructive math. And it would be now, of course, interesting to look at further results, or whether there are further results from computability theory that can be turned into interesting results from constructive math. So far from my side for the moment. Thank you very much.
Yeah, thank you, Felix, for the time, and thank you very much for sticking so well to the time. So we have some time for questions, so please go ahead. Simon.
Do you already have an idea of other results from constructive mathematics that you can potentially prove using this route? Or at least, I don't know, goals where you think this would be interesting?
To be honest, not yet. We firstly looked at those direct proofs and not directly in computability theory, but I think it would be definitely worth also to have an eye for ourselves at this question.
I have one question. So you have three different proofs of this theorem.
Mm-hmm.
So they give you functions, and those functions you could potentially run.
Yes.
Is one more efficient or better in some other way than the other? Did you think about that?
Efficient in what sense?
I don't know. If you try to run it with random inputs and then see how long it takes if you run the extracted Camel program.
So we haven't done this yet. So from my feeling, of course, this canonical last function is for at least the proof. So the proof that we wrote in Coq is the easiest one. So probably it might also be the most efficient construction, but I'm not really sure.
Okay. Well, it would be fun to see. Any more questions?
So I'm curious, do all these three proofs have a shared sort of underlying helper lemma code base, or were they all quite distinct?
So they all of those use results from the standard library, and the back and forth method that is used for the first two is somehow the same, but basically they are all for themselves quite compact in under 300 lines of code.
Okay. Thank you once more for the talk and for answering the questions.